Hello and welcome to another episode of Twimmle Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, I'm joined by Clare Gollnick, CTO of Terbium Labs, to discuss her thoughts on the reproducibility crisis currently haunting the scientific landscape. For a little background, a Nature survey in 2016 showed that more than 70% of researchers have tried and failed to reproduce another scientist's experiments, and more than half have failed to reproduce their own experiments. Clare gives us her take on the situation and how it applies to data science, along with some great nuggets about the philosophy of data and a few interesting use cases as well. We also cover her thoughts on Bayesian versus Frequentist techniques, and while we're at it, the Vim versus Emacs debate. No, actually, I'm just kidding on that last one. But this was indeed a very fun conversation that I think you'll enjoy. Okay, you all know I travel to a ton of events each year, and the event season is just getting started for me. On Friday, I'm on my way back to the Bay Area for the Scaled ML Conference and NVIDIA GTC. But the event I'm most excited about is my very own AI Summit, the successor to the awesome Future of Data Summit I did last year. This year's event takes place on April 30th and May 1st and is once again being held in Las Vegas in conjunction with the Interop ITX conference. This year's event is much more AI focused and is targeting enterprise line of business and IT managers and leaders who want to get smart on AI very quickly. Think of it as a 2-day no-fluff technical MBA in machine learning and AI. I'll be presenting an ML and AI bootcamp, and I'll have experts coming in to present mini workshops on topics like computer vision, natural language processing, conversational applications, machine learning and AI for IoT and industrial applications, data management for AI, building an AI-first culture, and operationalizing machine learning and AI applications and systems. For more information on the program, visit twimmleai.com/AI Summit. And now, on to the show. All right, everyone, I am on the line with Clare Gollnick. Clare is CTO at Terbium Labs. Clare, welcome to This Week in Machine Learning and AI.
Thank you. I'm happy to be here.
So you've got a background in neuroscience and biomedical engineering, but you've ended up spending a lot of your time working in data science and machine learning. Can you tell us a little bit about your path?
Definitely. So my background, my graduate school research was actually in information processing and neural networks, but not artificial neural networks, not neural networks that data scientists are usually talking about. And so it was definitely an interesting transition, leaving graduate school, spending all my time trying to figure out how the brain works, and then coming into data science and hearing people say, like my algorithm works just like the brain. And I was like, wow, interesting. You should tell the neuroscientist how that works. But it was it was an interesting transition. It's definitely a different type of problem and a different way of using data to make the world better. So in science, you're trying to learn so that you, in particular in biomedical engineering, to help cure diseases. And now I work in cybersecurity. And so you're using data and fighting another hard problem. It's just a very different type of problem.
Can you tell us a little bit more about your graduate work? What was your research there?
Yes. So we studied how your brain processes sensory information. So after, light touches your retina or something touches your skin or your somatosensory system, how is that information propagated through neural signals, through spike trains, and how is it that eventually that turns into perception would be the big question. And interestingly, with the engineering bent, the question was, using this knowledge, could we replace this sensory signal with artificial signals so that we could mimic sensory input for people who have lost it? So for example, if you've lost a limb and you no longer have your sense of touch, could we replace that, for example, was a long-term goal.
Interesting. And now when you're looking at this as a scientist, a neuroscientist, are you exploring it from at the level of chemicals, or are you looking at it, or were you looking at it more from a system level, electrical signals, or all of the above?
Yeah, so we used a couple of different signals, but broadly we're operating on the like spike train or neuron level. And so I like to think of it as, a non-natural language. What is the language of the brain? And the best current model for understanding how information is transmitted in the brain is through neuron spiking. And these patterns of spiking and the different neurons spiking at different times to represent different patterns that could create different perceptions.
Do you find it in working in data science and talking with data scientists that there are things that you learned about the brain and how those types of networks work that you feel would be helpful if they were more broadly appreciated within data science?
That is an interesting question. The thing that I find most fascinating is how these two fields interact. One of the things that is true is that we don't know how the brain works, and often we're using mathematical frameworks and we force that onto our model of the brain, and we see if it's a good model for predicting, for understanding the brain activity. And so it's a weird interplay where you would in many cases prefer it to be more from the brain to feeding the statistical modeling and the network modeling. But often it goes the other way around. A new statistical estimation technique is developed, and then it is applied backwards into neuroscience. It is an interesting dynamic because you would imagine or hope in some cases that it went more the other way.
Right. Especially going back to your comment how people talk about artificial neural networks as being brain inspired when it often happens the other way around.
Yeah, it can. I definitely see it going the other way around very often.
Awesome. And so you've been recently spending some time thinking about kind of going back to your roots in science, the reproducibility crisis that has been much talked about in that field and what data scientists can take away from that. Maybe start by talking about that reproducibility crisis for folks that aren't familiar with it.
Definitely. So I would say that the reproducibility crisis is a little bit controversial, but the main observation is that a lot of the literature that has been published, a lot of the experiments that have been summarized and the results that have been summarized, in particular in the fields that I was in, so in biology and neuroscience and in psychology, is not reproducible. Meaning that if you were to pick a paper out of the literature and try to perform the experiment as exactly as set out in the methods, you likely would not achieve the same results as the authors report.
And do you say it's controversial? Would you say it's controversial that it exists or because it exists?
I think it is controversial because it implies that the methods that scientists are using are not actually objective or perfect. And a lot of scientists work very hard and their work is very close to their identity. And so the implication that the body of work that a lot of very hardworking and well-meaning scientists have put out into the world is not reliable as a body of knowledge hits a lot of people really core to their identity. Mm-hmm. And I think the way that it's controversial, it comes from that sense of ownership over this body of literature.
Mm-hmm. Is it generally accepted though that it's a problem, or is that still up for debate in scientific corners?
I would say that the fact that there is a problem is no longer debated. The scale of the problem is still up for debate.
Mm-hmm. When I've heard about when the topic of the reproducibility crisis comes up, a lot of times you hear people throwing around like p-values and the implications of that. What's that all about?
That's very interesting. So I can talk from my own experience about how I was taught about hypothesis testing and p-values being a part of that. And I think it's interesting because I see a lot of parallels to the way that data science is taught now. When I was in high school, I learned about hypothesis testing, and I thought it was the coolest technology that anyone could possibly imagine, because I so desperately wanted to be a scientist, and I knew that scientists needed to be objective. So I needed this objective way to take an experiment that I ran and then know whether something was true, whether my experiment was meaningful. And the hypothesis testing was just so compelling as a tool, because it basically allowed me to just take this data and run it through an algorithm and then have an answer.
Mm-hmm.
And what is interesting about that is that now these hypothesis tests are at the center of the controversy over the reproducibility crisis. And a lot of people are attributing them, and I agree that it's a major part of the cause of the reproducibility crisis. And one of the most interesting things about it is that it's actually a problem of scale, that p-values and hypothesis testing applied across many scientists simultaneously or over and over and over again on the same data set. That's a process we now call like p-hacking.
P-hacking
is actually, so like reanalyzing the same data over and over and over again until you find something that appears to be statistically significant. And that's now considered one of the major problems and major causes of the reproducibility crisis. And what's interesting is that really machine learning is exactly that, right? It's reanalyzing the same data over and over and over again, testing hypotheses in a very, very faster than even any human or any scientist normally would be able to, and then trying to pick the one that best explains your data. And so there's a lot of parallels between these hypothesis testing and machine learning.
So with that in mind, how should it impact the way we approach data science?
That is an excellent question. So one of the things that is true about how machine learning is taught is you're always taught to cross-validate, which means that you hypothesis generate on a training set of data. You run all those models, and then you test that data once. And that it's interesting is that testing this model once on a new set of data is a lot like making a very specific prediction and then running that experiment, which is what the scientific method is and its best formulation. Make a very specific prediction that is unlikely to occur unless your hypothesis is true, and then run the experiment and see if that actually happened. And so in a lot of ways, cross-validation is taught and is meant to solve the problem of machine learning being essentially p-hacking.
Okay.
And what's interesting is when you think about it that way, you realize that a data scientist who is well-meaning and trying to make a model really, really work, could essentially start p-hacking their data by repeating this training and testing over and over and over again. Sometimes people call this, overfitting on your test set, but it's also just another formulation of p-hacking.
Right. Interesting. I guess what's kind of throwing me about that description is that it's also, I think, called data science, right? That's what people are fundamentally doing is trying to manipulate, models and model parameters, through an iterative loop to try to come up with something that works. Yeah.
So what's really fascinating is, so I became very frustrated with this when I started researching. The reproducibility crisis was the thing that got me interested, but it led me into this sort of academic deep dive into, why? And I ended up eventually studying the philosophy of data and why is it that we believe that we can learn from data at all. And what I learned is that there's a couple important assumptions that you're making implicitly when you think that you can learn things from data. One of the most important ones is that if you think about it, 100% of the data that we have ever collected is about the past.
Right.
We don't have data about the future.
Right.
But most of the time, we're trying to learn something about the future.
Right.
We're trying to make predictions about the future.
You're assuming some kind of predictive value or dependence.
Exactly. You're making the assumption that something about the past and the future is shared, or that there's a shared set of rules in the past and the future. That means that you can learn something about the past and use it to predict the future. And one of the things that's interesting is that if you think, what is the counterfactual to that? What is the opposite of having rules? Potentially, things just happen due to chance, right? Perhaps things that happened in the past just happened and there wasn't a rule. So when you choose to use data to try to make predictions about the future, you're implicitly saying, I believe the system that I am studying is determined by a set of rules, and I'm just trying to figure out what those rules are. And what's really cool about what's really interesting is if you think about the ways and the problems in which machine learning has been the most successful, they're all in the types of problems that are extremely rule based, or more often where humans determined the rules. For example, the first example is chess, right? The very first example of automated intelligence.
Mm-hmm.
Chess is a entirely rule-based game that they're playing. And one of the great parts about it is that about making this a tractable problem and making p-hacking not a problem is that you know the game you're playing, you know the rules. And if someone tried to tell you, oh, I'm going to move my pawn and I'm going to move it, 7 spaces diagonally to the right, you'd say, oh, no, that just breaks the rules. You can't do that. And because it's rule-based and tractable like that, it's actually machine learning ends up being and automated intelligence ends up being a much more powerful tool in this type of problem than one in which the rules are not known to exist.
So what's an example of a system where the rules aren't known or known to exist and machine learning doesn't work as well?
That's an excellent question. So I have a couple, but one of my favorites to talk about is actually talking about moving a problem along a spectrum between being very rule-based and not rule-based. It's not quite machine learning, but it certainly is predictive, and that is predicting elections.
Okay.
Elections in the U.S. are rule-based, or they have been historically, which means, one person, one vote. The definition of state boundaries are determined by a governing body. And the amount of electoral votes or number of votes that these states get is determined in advance as a rule. And at the end of the day, what you end up predicting or measuring and predicting is just a few parameters, basically who will vote and who they'll vote for. And that makes it a very tractable problem for predictive type analytics, whether it's machine learning or your Bayesian approaches or however you want to go about it. An interesting thought experiment is to say, well, what would happen? How would we predict elections if those rules didn't apply? For example, if you didn't know how many votes each person got and you had to infer that as well, or if you didn't know what the state boundaries were and you had to use data to try to guess based on previous elections that you've seen as outcomes what the state boundaries were, how much harder would this problem be? Or worse, if you're not in a functioning democracy where rules matter and votes can just be deleted and removed or added or stuffed arbitrarily, randomly, then what use is your predictive technology? What use is data at figuring out what the next outcome would be?
And so what does it tell you to explore, these alternate scenarios where the rules don't apply?
So my favorite use case, like practical use case of this philosophy and this understanding is to think about what framing the problem means. So you'll often hear people say, oh, it's all about how you frame the problem.
Mm-hmm.
Often, if you ask them, well, what does that mean? How do you frame the problem? It's hard to articulate what that is. For me, what understanding about this problem of needing a rule-based system in order for learning from data to be a practical solution, you have to think about when you're framing the problem, you're trying to frame it so that the rules apply. So if you have a choice, if you want to choose potentially multiple different ways of framing your problem or setting up your model or your features, right? You're trying to pick features that are representative of true rules about how the domain actually works. Mm-hmm. It's basically an argument for domain expertise.
Okay.
It's not at its surface. It's basically like understand the system that you're using because that's what you need in order to make good models. And I don't think that that's particularly controversial. But it does suggest that you can't just add a bunch of data into a model and then press go and get the meaning of the universe out on the other side.
Mm-hmm. Is there an example from your experience at Terbium where a given use case, maybe there was an initial temptation to approach it without thinking about the underlying rules and in kind of applying this philosophy and thinking about those rules, it changed your approach to modeling and your outcome?
Yeah, that's an excellent question. So Terbium broadly works in the field of cybersecurity. So speaking a little more broadly than Terbium specifically, this is a problem that people in cybersecurity come up against all the time, which is that hackers are not rule-based entities. when they try to get into a system, they're trying to break the rules.
Mm-hmm.
So sometimes you have a choice. You have a choice of trying to learn the rules, or you have a choice to try to set the rules in your system. And so, for example, you could choose to try to learn how a network or a given company's network works, and then try to detect anomalies, and in order to use those use machine learning to detect anomalies. And that approach will work, but it's hard. It's hard because the way the network interacts is changing all the time. The rules are changing. Which computer is talking to which computer are changing. But another way to approach the same problem is to set really good policies on your network, essentially permissions policies, and make those rules extremely formalized and designed by humans. Like, this computer can only talk to this one. Like, this is the rule. And then when you start observing anomalies, when you have a network that is really well designed, in which that you have all the minimal access to any particular resource, then data suddenly starts working a lot better at detecting bad actors on your network, for example.
Okay.
So you have a choice of, I can just learn the rules as they exist, or I can create the rules. And then data suddenly becomes much more powerful as a tool if you create the rules.
Right. It sounds to me like a combination between the previous point you were making about the importance of domain knowledge, but also just the utility of constraints in making a problem manageable, which I also don't think would be necessarily controversial as a point. But it's interesting to kind of layer it onto this way of thinking about data. You mentioned that you started researching the philosophy of data. Where did you find research about this, or who's out there philosophizing about data?
There's a lot. It's actually fairly interesting. I'll tell you some of my favorites.
Okay, please.
So David Hume wrote about a long time ago about the law of induction. And a lot of these are philosophers. And so instead of talking in the concept of data, they're talking about thought experiments. That's their usual unit of work. And he posed a famous thought experiment that asked, how many times do you have to observe the sun rise to be certain that it will rise again tomorrow?
Mm-hmm.
And this is a really compelling and interesting question for me, because the question is essentially, how much data can I collect before I'm certain?
Mm-hmm.
If you think about that question, right, it gives you this deep sense of like, wait, what? Like, does this actually work? So that's one writer I really like. Another one is Karl Popper. Karl Popper is famous for a lot of things, but one of the things that he did was come up with the concept of falsifiability. So in science and in data-driven endeavors in general, you never prove anything true.
Right.
You just demonstrate that your best idea or your best model is not yet false.
Mm-hmm. And
I was taught this in high school, and I thought it had existed since something like the beginning of time. I thought that this was had come up, thousands of years ago as like the nature of knowledge. But it turns out that this concept of falsifiability that's so central is actually from like the 1960s.
Oh, wow.
It's much newer than you could have imagined, than you would think. Yeah. And that just gave me this feeling that like so many of the techniques that we've been using and the way we've been thinking about data and this entire endeavor to learn about our world using like this systematic collection of data is like very new in the world of like philosophy and how you learn from data. So it was very fascinating. So those are two of my favorites, but I'm always looking for more.
Yeah, it's interesting. Hume, obviously, I associate with philosophy, but never would have connected that question to one of data explicitly, although it's obvious now that you say it. If anyone else who's listening to this knows of some others, definitely send them my way. It's super interesting. So reproducibility crisis kind of led you to thinking more broadly about data and some of the implicit and explicit assumptions we make about data. One of the thoughts that I had when you were describing this, the inherent belief in that there are rules that govern our data is kind of brings me back to the whole Bayesian versus frequentist thing. Like the implication is almost that, there's no such thing as a non-Bayesian.
Well, yes. The way I like to think of it is that I think Bayesian statistics as an approach is much stronger than frequentist statistics, but it doesn't actually solve the problem because in order to make a prior, in order to frame it, you're still making a lot of assumptions about what matters in the problem. So what's fun to do as a thought experiment, I think, again, Bayesian is just a much more powerful technique, but it still requires you to make this like initial guess on how the world works. And that's, again, that rule-based thing. Like you have to assume that there are rules. So it's interesting.
Right.
Yeah.
And so did you, to kind of come back to the implication for data scientists about this reproducibility crisis, like, do you have, when you talk about this, is there like a prescriptive list at the end that you do A, B, and C and you'll be clear, you'll avoid the fate of these poor irreproducible scientists? Or is it not that clean?
Well, so what I say is data is not magic, and you just have to be okay with that at a certain extent. You have to think about data and inference as some of the tools in your toolkit that you can use to approach a problem, but not necessarily always the answer. The second thing that I say is this is for people who are in the position of making strategic investment in data products. So, for example, VCs or even managers, and you're trying to understand which of these solutions that someone has put in front of me is most likely to actually generalize and actually work when put out into, either as a company or as a new model for your software or your platform or whatever it is. And at that moment when you have to make a choice, a really important question to ask is, how did you make this model? Like, what was it that made it work? And a warning flag for me, being in this position all the time, like having to make a decision about where to invest our company's resources, is to hear a data scientist say, I just ran 17,000 different algorithms in different tests, and I did a huge grid search across like all of the parameter space, and I found the one that performed the best. Because to me, that sounds like p-hacking. And it has been proven out in my experience that that's a riskier model to choose to put into production. Then alternatively, if someone comes to you and they say, how did you make this model happen? What was the thing that mattered? And they come and they say, hey, like I thought really hard about the problem. And when I realized that if you look at the problem differently, if you look at it this way as opposed to this way, then everything made sense. Then my model that didn't work suddenly started working. And to me, that sort of, I reframed the problem, and then I didn't have to work as hard to find the right answer. I didn't have to p-hack. I didn't have to really push, beat my data in order to get an answer. That is a sign, I think, of a model that's much more likely to work when pushed into production or when you invest in a model.
Is there an implication there that you're not a fan of like deep learning? Like a lot of the way I think the deep learning camp thinks about the world is like throw a huge amount of data at this neural network and, let the network figure it out. And we shouldn't have to, in kind of the purest sense, like we shouldn't have to bring a lot of a priori knowledge into the way that we, build these networks or like, process the data or what have you. That's the role of the data and the network to figure that stuff out.
You have me pegged at what I call a deep learning skeptic. I would say that much like any tool, there are specific situations in which I think that could be a really interesting approach, but that it is not a panacea to all problems. And I don't believe, based on my understanding of philosophy and based on my understanding of the assumptions that go into the process of learning from data, that there will ever be a modeling architecture or structure that avoids this process or makes this problem go away. Until, like, what would it take? It would take a new system of logic, something different than our current definition of inference. Certainly a solution to Hume's law of induction, so to speak, before whatever new algorithm or new approach comes out. I would think that it was a revolutionary change to how we solve these problems.
I know it strikes me that you're also saying something about, the role of optimization. Like you can, your example with like, grid searching your model to death, so to speak. Like, is this kind of philosophy, does it undergird a belief that, that there's some inflection point where your 90% model that's based on fundamental principles, is, way better than your 95%, performing model that is kind of brute forced when you try to actually put it into production?
Yeah. So, I mean, this is where it gets hard, right? So what I would say is what you learn when you study philosophy and learning from data is that the pursuit of pure objectivity is a fool's errand in some way. But so why do you do data science? Well, you do it. Why do you build these models? It's because they're useful. And what I do think is true is that there's potentially diminishing returns in the last 90 to 95%. But that's not true in all cases. In some cases, I always say, like, you don't make decisions based on probabilities. You make decisions based on expected value. If you have a use case where failing is so catastrophically terrible that you can't risk that extra 2%, then it might be worth your time and effort to try for the hopes that it actually does work. And it is possible, to stumble upon the answer, even if it's not a rigorous process. It is possible to find it, right? It just means that it's not a robust way of going about it or a reproducible way of going about it, which is sort of the nature of the game. So it's really about understanding, what are you doing? Are you trying to sell like 5% more products? Are you trying to prevent 5% more crime? Like, how bad are your potential failures? And then deciding whether it's worth it to try to risk it to do this brute force approach. But if you have the option, like, you only do that if you don't have the option to solve it by understanding something fundamental or rule based about the problems. That should always be, in my opinion, your first step.
Sure.
In building a model.
Now, we've talked about the reproducibility crisis in science and applying that, the lessons learned there to data science. You also hear from time to time, talk of reproducibility issues in data science, meaning in the machine learning research, the difficulty going from a research paper to a working implementation. Any thoughts on that?
Yeah.
That was a very heavy, yeah.
My feeling about that is that it's probably my guess. I've seen the reports of this. I have not myself tried to reproduce some of these core central papers, but my guess, if I were to make a guess on what the cause of this is sort of rooted in the same idea, where if it's applied to the right problem, a problem that has a good formulation of rules, it probably works the way the person presented in the original paper. And then if you take the exact same use and you tweak that problem even slightly, like sometimes that problem could just be like where you got your data from, because the rules no longer apply in quite the same way that they did because of how you collected it or because of your bias or some amount of data that you're missing for whatever reason. And that might explain some of the lack of reproducibility. In the same way, that the reproducibility crisis in science might be explained in some part by people not reproducing in exactly the same way, not using exactly the same materials, not doing things with exactly the same technology, right. that some of that variance might be explained. And what that's really saying is that you were relying on rules that weren't actually core and central to your problem, but they were artifacts. They were, extra things, like my technology works this way. And so this worked in this case, as opposed to this other case, it didn't generalize in the same way as I expected it to.
Yeah. It strikes me that there are a number of things going on there. I think there's the case that you mentioned where I'm trying to apply this paper to my use case, and all of the things that you mentioned apply. It also ties back to, I should say, the kind of issue that Ali Rahimi brought up in his NIPS presentation. You may have heard of this, where he kind of decried the lack of rigor in the field, or at least certain parts of the field, specifically, I think, talking about deep learning. And that kind of ties to reproducibility, and that, people will publish papers, there's not a set of kind of fundamental rules for how you got your architecture or your hyperparameters. You just have them. If you don't share them with anyone, then they can't reproduce what you did, because they're like magic numbers that you just found in your grid search.
Yep.
Right?
I think if we could learn anything from how poorly the scientists are handling the reproducibility crisis on a human level, I would suggest that when we try to solve these problems, we do our best to not throw stones or name call or point out individuals, and talk again about the problem as like, hey, this is how data works, and we have to know this about the tool that we are using going into it, so that it doesn't feel like a direct attack on someone who's trying to make things work with the tools as they understand them. I think a better solution to this problem is to raise the awareness of the idea that, hey, like, this doesn't actually work. We all want it to work, have data, magic formula, and then we know things, but it doesn't. And it's actually harder than that. And we all have to be okay with that when we approach it. Awesome.
Any closing thoughts to kind of tie things up for us?
No. I think I would
Which
say
is a totally valid answer.
Yeah, I guess I do have one closing thought, is that another really great thought experiment to look into is the infinite monkeys theorem, or infinite monkeys thought experiment. It's a really good demonstration of what happens when you scale up inference.
And explain that.
I love this thought experiment. So it goes basically like this. You walk into a room, and there's a monkey, and the monkey's on a typewriter. And the monkey's banging around on the typewriter, and you look at what the monkey is typing, and you see, hey, look, this monkey has typed all of Shakespeare's Hamlet. And you think, oh my gosh, like, this is so crazy. Something must be up with this monkey. There has to be a rule to explain why this monkey happened. Clearly, this monkey came from the alien overlords down to earth to rewrite Shakespeare's Hamlet. So you're very surprised by this. But then someone tells you, hey, if you had gone over to that room over on your left, or the one over on your right, you would have seen another monkey. And in fact, there's not only one monkey, but there's actually millions of monkeys, or billions of monkeys. And they've been typing on these typewriters for as long as anyone can remember. And every day we've been looking, and we've been looking, and we've been looking, and we've been just trying to find that monkey that had typed something that we thought was compelling, that looked like there was evidence of a rule. And we finally found it. And then you think, oh, well, it's not thing about this monkey. It's not the fact that this data happened or this data was collected, but how we came to find it. And so one of the things I like to always say is when you're trying to evaluate how solid your evidence is, you should ask how many monkeys. You want to know how many times you had to look to try to find it.
Nice. You're going to have to find a way to work that into the title of this podcast. How many monkeys? Awesome. Well, Claire, you've definitely given us a lot to think about. Thank you for taking the time to chat with me.
Thank you. It's been great.
All right, everyone. That's our show for today. For more information on Clare or any of the topics covered in this episode, you'll find the show notes online at twimlai.com. If you're new to the pod and like what you hear, or you're a veteran listener and haven't already done so, head on over to your podcast app of choice and leave us your most gracious rating and review. It helps new listeners find us, which certainly helps us grow. Thanks so much for listening, and catch you next time.